with respect to the calculus part, it's gonna start with the derivatives and then integral, right? So how did we define derivatives? Just recall, I would say the first important concept in calculus is that derivative is the rate of change, the instantaneous rate of change. Okay? So if you draw in the figure, it's going to be the rise of a rod, which is slope of tangent, and the notation is df dt. That's the Leibniz notation. Or you can put it as f prime of t, where f is the function, f prime stands for the derivative function. And the definition is the limit when delta t, the change in the variable, the change in input goes to 0. You want to calculate the average rate of change within that change of the input. So the input changes from t to t plus delta t, okay? And then the changing the output is just the functional difference, and the changing input is delta t. So, or if you want to write it as t plus delta t minus t, okay? So that's exactly what you can have in the denominator, which is of course delta t. So basically, this is the definition of the derivative at whatever point t. Right? So this is in terms of the physical context. This is the instantaneous rate of change. So this is actually an average rate of change when the input starts at t and ends at t plus delta t, right? So in a figure, if you have t as the horizontal axis, f of t is the vertical axis, and the function is something like this, then at whatever point, if you want to do the derivative is actually the slope of the tangent line. That's the instantaneous rate of change. Tangent line. And then derivative is actually the slope of that. And slope is what? Slope is the slope of a line is just of course the average rate of change, which is rise of a run. But now, how do we calculate the slope of tangent line? So if you think about it, on a curve like this one in black. So if you are drawing the tangent line, locally speaking, it will only intersect this curve at one point, right? That solid point right there. So what have we done? In calculus, we use secant lines to approximate the tangent. So basically, you pick another point along the curve, and then you push that point closer and closer to the point that you're looking at. Right? So basically, this is the point that you're looking at, which is B. Right? You pick another point, and you make that other point closer and closer towards this point. And this is the input T. This is the input T plus delta T. Right? So this part is the change in input, which is delta T, which is also the run. Right? And then the rise is exactly the change of the output right here. Right? Yes, I probably want to make it a little more curvy. So this is run, delta t, this is rise, which is f of t plus delta t minus f of t, right? So the higher point, this y value or the function value is the latter output minus the previous output that gives the rise, right? So when you are using these 2 points to approximate the tangent line, this slope of the segment is this thing, right? So you have 2 points that you can construct a line, right? That line segment, the slope is what? The slope is just right over run. So that's the fractional part. And then when you take the limit, what do? Actually, you push this point closer and closer to the original point. And then that's just using this secant line, okay? Using the secant slope to approximate the tangent. Okay, now what happens if we are looking at the vector function? So just notice it's a little bit different because this the derivative f prime is actually the slope of the tangent that we're looking at, which is the slope of this line, right? And that's geometrically speaking not so straightforward. So we were using the secants. But now to define the derivative of a vector function, the notation we can just replace this f by that vector function r. Right? So the derivative can be written as dr dt. It can be also as r prime of t. And now we just follow the limit definition above. So this is still the limit when the changing input is delta t and it goes to 0. The average rate of change. Okay. Well, the changing output is going to be a vector, right? And then you're just dividing by the changing input, and you want to know the rate of change. But this thing is different in the sense that this is a vector. So the division will give you a vector, and then you take the limit, it will give you a vector. Okay. So here, r prime is a vector. Right. Now, geometrically speaking, it's slightly different from what we have seen above. So, okay, so to think about the points we're looking at, so let's say this one. Let me put it here. So this is RT. Okay, so this is the vector output that we have when your input is t. Okay, and now if you change the input, then you'll be ending up with another vector somewhere like right here. Okay, so this is your r of t plus delta t. And now, if you do the vector difference, actually we have a vector, and it indeed associates to that segment, because the latter output minus earlier, that gives us what? Gives us this one, okay? Triangle rule. Yeah, let me make it purple. Okay. So this one, this r of t plus delta t minus RT. Okay. So this is the vector right here. And now if you look at this, okay, this is actually well, this is actually the vector constructed from the segments, okay, lines. So when you're doing this limit, okay, that's going to be really similar to what we have seen, because now we have the line segment right here, and we're pushing it closer and closer. We were pushing these 2 points closer and closer, right? Then essentially we're using the secant line to approximate tangent, right? So if you follow the idea, if we push delta t to be 0, and then it's also gonna represent the direction that is tangent to our curve. Okay? So that's space curve like this. Let's control this thing. So one vector of t, the other one vector of t plus 17, and right. So we just had a difference, which is this, right? But that's the secant vector. Okay, so this is the change in output. But now, like we said, if you push, move this a little bit to the balance. I need it to be more space. When we push delta t to 0, okay, so what does that mean? That means this point is going to get closer and closer to this original point, right? And so the direction of the secant line will get you the direction of the tangent line. So what's the direction of the tangent line? So the tangent line, okay, it always follows the direction of your curve. So basically think about it. When you're traveling along the space curve like this, okay, so this is really like driving a car on a really long bridge that's just following along the direction. Okay, so at whatever point you have, to stay on this long bridge, you need to follow the direction of the curve, and that's actually this one. Okay. And let me draw it a little bit longer. Okay. So tangent direction. Okay. And that's our vector, our prime. Okay. So the tangent direction is just like what you have seen before. So you're using the secant line is in 2D to approximate the tangent line in 2D, and in 3D it's not really different. Remark. Prime T is called the tangent vector, which is kind of like a generalization of the tangent line. We also define the unit tangent vector. So basically, if we only care about this direction, we don't care about the magnitude of our prime, then we actually isolating a unit vector out of it. Okay? So it's going to be a vector along this direction, but the magnitude is 1, right? And that's going to be named as R cap T. Okay, it's capital letter T, and this has a magnitude of 1. That's the unit tangent vector. So how do you get the unit vector? You just divide by the magnitude, right? So cap t of t is defined as the derivative, which is a vector function we divide by its magnitude. And it looks complicated, right? Because now if you think about it, you have this vector function r prime, that's what you differentiate. That's the result of differentiation, component-wise. But then the magnitude is what? Is the square root of the component squared, added up. Okay. Theorem. That Rt should be the vector function f of t, g of t, h of t at the components. If f, g, and h are differentiable, if they're differentiable, then the vector, the derivative function r prime is just the component-wise differentiation of the original vector function. So this is what we expect, right? So in Calc 1, we know how to do the limits of a function, right? And then we know how to differentiate, and later we learn how to integrate, okay? Do definite integrals or indefinite integrals, and many other stuff. But here, for vector function, when we take the limits, we take component-wise, and then when we do the derivative, it's all the component-wise. Okay. So let's look at an example. Consider the curve, space curve Rt. So now we have square root Ti plus 2 minus Tj. And then that's all. So we don't really have a k. So that just means we only have the xy coordinates, and z coordinate is always at 0. Okay, so this is still a two-dimensional. So there's a curve within a plane. Right? So we want to find R1, so point on the curve, the tangent direction along the curve at the input 1, and also t, cap t, the unit tangent direction at the input 1. Okay. So here, note that we have x component equals to square root t. The y component is 2 minus t. So this is a parametric equation, right? But then if you think about the relationship between x and y, you can say, okay, I can eliminate t by just saying t must equal to x squared, and then I substitute that into y, right? So eliminate t, we have actually y equal to 2 minus x squared, exactly the way that we do the elimination. Okay, this is in R2. Since in this situation the z coordinate is 0, so we are actually lying within the xy plane. Okay, and then yeah, well, before closing the bracket, let me just quickly sketch the figure. So basically, within the xy plane, we have so this is y equal to 2 minus x squared. This is parabola opening downwards, and this is symmetric with respect to the y-axis, right? Because we have just 2 minus x squared, so this is an even function.
Okay? And what do we have? So basically, when t equals 1, we're looking at R1. So the curve is this black curve, but then when t equals 1, we are at 1 x equals 1 and y equals 1 as well. So that's actually the point right here. Okay. So that's our 1, right? And then we can expect that the tangent direction is actually this. I'm going to put it in black. So the tangent direction is just along the tangent line. Okay. And if you think about it, here when t increases, my x value gets large, right? So my y value gets less and less. So here it's along the tangent line, but then we're going down. Okay. So that's r prime of 1. But then the unit tangent direction is exactly this one. So basically, we don't really know the magnitude of r prime, but then we just we find the unit vector that's along this direction. In fact, okay, so it could be something like this. But the idea here is just this, right? Without the explicit calculation, the figure just gives you this kind of relationship. And then here I close the bracket. And now let's do some calculations. Okay, so here it's firstly we need to calculate the substitution where t equals 1, and we have done that already. So that's actually just I plus j. Because when t is 1, both components are 1. And then our prime of 1 is exactly when we do the derivatives at every component, and then we evaluate at t equals 1, right? So basically, where square root t is if you want to write it again, write it in other words, this is t to the 1/2, right? And then this is the power function, you're using the power rule, so the derivative for the x portion is 1/2 square root t, okay, so 1/2 t to the negative 1/2, exactly this, okay? I, and now 2 minus c has a derivative of -1, okay, so minus j, so minus -1 in front of j, okay? And then we evaluate at t equals 1. And now in our multivariable calculus, it's very important to always indicate which variable you are evaluating. Because now we see we have x, y, although in this situation we don't have z, but it's likely to appear, right? Then we have parameter t, right? In the future we have more variables. Okay, so when you're doing the evaluation, specify what you are evaluating. And then you can just plug in t equals 1, and then you see this is 1/2 I minus j. Okay. So this is that black vector in our figure above. So that's good. So if it's so good, then the unit tangent direction is just normalizing r prime. Okay. So of course, if you just look at this vector, okay, so this vector that definitely has a magnitude that's larger than 1, because j component has -1 already, right? So, but we want to get a unit vector which has a magnitude of 1, so we just normalize by dividing by this magnitude. So t, cap t is r prime, just divide by its magnitude. So the numerator is this 1/2 I minus j, and the denominator is the magnitude of that. So square root of the sum of the components squared. Okay, so 1/4 is the square of 1/2, and 1 is the square of -1. So essentially, we have square root of 5/2 on the in the denominator. So yeah, let me write just this step here. So square root of 5/2. Okay. So if you do this division component wise, there's going to be 1 over square root of 5 I minus 2 over square root of 5j. Okay. And that's it. Any questions so far? So you see, component wise derivative is tangent direction, right? And then normalizing it gives you the unit tangent direction. Okay. That's straightforward. And now, second derivative. So basically, if our derivative is the component-wise derivative for the space curve, then the second derivative will just be the component-wise second derivative. Okay. So just a double prime of t equals to. So here we still assume that f, g, and h. So it's the same thing, right? F, g, and h are components. So it's going to be component-wise second derivative at f double prime g. G double prime of t and h double prime of t. And then let's look at some properties. So basically, to summarize in one sentence, the thing here is that as long as every component is a univariate function, so the derivative rules, the integration rules are going to be carried through for the tangent. So yeah, so let's just write things down. So firstly, if you do the derivative of the sum of two vector functions or difference of the two vector functions, it will be the derivatives take the sum of the difference. Okay. So this is exactly so. If we want to write the easier notation, this is just u prime t plus or minus v prime t. Okay. So this if it's sum, then you're having the derivatives summing out, and then if it's derivative of the difference, it's going to be the difference between the derivatives, okay, respectively. And then if you have a scalar multiplication, let's say a constant c multiplied to the vector function u again, and you can expect that you can drag this constant out. So this is going to be c times the derivative of u, which is u prime. Okay. And then the product rule, of course, it will still be the same thing. So, but so here we need to mention that the product rule has a few versions. So let's take a look at one of them. So just think about the c. Now we replace it by some scalar function. Okay, so that's the simplest case. So let's say we have L of t times u of t. So here, this is a scalar function. And here, this u is the vector function, but we know that this has a vector value. So this is a vector value function. So basically, if you think about it, this is essentially saying what? So for you having the XYZ components, this L just multiplied to every component, right? This is going to be X L LX L well, excuse me. Let's say if they are FGH. So it's going to be LF, LG, LH, right? So if you want to derive everything, you just do the product rule component wise. But then you will see that somehow L will appear at every component, so that can be dragged out. So here I'm just going to directly do the final answer. It's going to be the same thing. The derivative of the first times the second plus the first times the derivative of the second. Okay, so it's gonna be L prime, which is a scalar function multiplying by the second, which is a vector function, plus the first multiplying by the derivative of the second. Okay, so it's not really hard to do for this kind of a algebraic process. Okay. And it also is true if you have two vector functions starting with each other, but that order will be very important. Okay, so if you're taking the derivative where you have u of t starting with v of t, so it's still going to be the same idea. It's going to be u prime starting with v plus u, the first, starting with the derivative of the second. And in this situation, you see, okay, u dotting v and the dot product is kind of more commutative, right? So you can interchange the order. But now, if you have a cross, then you cannot really interchange the order. So that's something slightly different. But if you want to memorize it, it's still the same rule. Okay, this is the product rule. So ut cross vt. U of t, the vector function crossing v of t, another vector function. So it's gonna be the derivative first crossing with the second plus the first crossing with the derivative of the second. Okay. So the above three properties are actually just directly applying what we have learned from Calc 1. So basically, if you want to verify it, you just need to, if you want to verify these, you just need to be careful when you're doing the arithmetics, okay? And of course, the product rule is really just extending what we have learned, right? I mean, what about the chain rule? Essentially, it's the same idea. So remember, when you have the chain rule, this is just a relation. So basically, you have a function that you compose with another function, right? But here we have a vector function. So basically, this is doing another parameterization. So basically, u of some scalar function, right? But then instead of a t, we have the L of t, which is just a scalar function that's representing the parameter. Okay. So this is a composition, right? So we can expect that this is going to be the same kind of a rule. So it's always the derivative of the outer evaluated the inner multiplying by the derivative of the inner. So let's just write that down. So the derivative of the outer, now we see u is a vector function. So the derivative of the outer is still a vector function. And so it's u prime. We evaluate at the inner. Okay? And then we multiply by the derivative of the inner. And we notice that a little l is what? Is a scalar function. So this part is scalar function. But this part is vector valued function. Okay? Vector. Valued. So you can expect that this L prime, this little L prime can be somehow put in the front. Okay, so this is actually a scalar multiplication. So this is exactly L prime of t. Scalar multiplying u prime evaluated at L. Okay. So if you want to put it in another notation, so namely, this is du. So we are doing the derivative of the vector function u. Okay, so du dt equals du dl. times dl dt. Okay. So here you can see everything is pretty much the same thing from before, except that here that function, the outer function u is now just a vector function. Okay. So in the old days, you just have du dt, du dl, or du dt equals to du dl times dl dt without the arrows of the vector functions, but now we just have those. Okay. Everything is pretty much the same. From Calc 1. Okay. Next one. So now that's these are derivatives, right? And what about the integration? So if you have a definite interval from a to b of our vector function of t, so that's still component-wise derivative, integration. So the definite interval from a to b, so basically we just integrate the first component. And then for the second component, we just do the integration on the same interval. And then for the last component, we do the same operation that the definite interval from a to b of a to b dt. And then we can expect that the fundamental theorem of calculus will also hold. Okay. So if our vector function r t equals to the derivative of some kappa, and we assume that both are continuous. What does it mean? This just means that our little r is a derivative of cap r. So cap r is an antiderivative of little r, right? So basically, what does it mean? It just means, okay, if you know an antiderivative cap r, then you can just evaluate the antiderivative function at the endpoints of your interval. So from a to b, the definite interval of little r, this equals to, so we just write it again as cap r prime, but then we just evaluate this antiderivative function at b minus the evaluation at input a. Okay, so this is the fundamental theorem of calculus. Calculus. And here cap t, excuse me, cap r of t is the antiderivative. Is an antiderivative of little r. And of course, if you now think about the antiderivative, similar to Calc 1, if you plus whatever c is still an antiderivative, right? So cap r is any antiderivative is good. Okay. Example. So here, so I would say we have a proof that we're gonna give about the unit tangent direction. This process is this kind of proof is not required, but it may help you with some kind of computation, because yeah, you will see what's going on. So prove that for any vector function, any curve of t at any t, where cap t, the unit tangent direction, and its derivative, cap t prime, are well defined. We have the following relationship that cap t, starting with its derivative of the vector function, always equal to 0. So basically, the idea here is that if you think about the space curve like this, so let's say we're just traveling along the curve like along this direction, okay, illustrated by the arrow. So basically, what does it mean? This means, okay, for whatever point on the curve, cap t is what? Cap t is the unit tangent direction. Okay, so basically, it's the unit vector that's following along the direction of your curve. Okay, and the length is always 1, right? So it just follow along the direction, and the length is the same. Okay, follows along the direction, and the length is the same. Okay, so that's cap t. Okay, it's cap t. And now here, if we think about the rate of change of that, this is t prime, right? So that's actually how you are changing the direction, okay, sort of saying. So if you think about, let's say, these 2 points, so somehow so at first, the direction, the tangent direction is like going to the right, but a little bit upwards. But then it changed a little bit when we had the next point, which is pointing towards the right, but pointing downwards a little bit, right? So in a sense that the change in direction is somehow like pointing downwards a little bit, right? That's representing the change in direction. So but here we're just trying to prove that the instantaneous rate of change for this black vector is exactly the red vector that's perpendicular to the back one. Okay, that's t prime, and that's t prime. And here we're just trying to show that and the black t and the red t prime, these 2 vectors are always perpendicular to each other. So here I just erase that bracket of t because I don't really want the same input to repeat. But yeah, you get the idea. Now let's give the proof. It's actually pretty neat, right? The proof. So recall that the unit tangent direction has a magnitude of 1. Okay. So somehow we notice that this is the only thing that we know about the unit tangent direction, right? So in general, it could be any direction, but we only know that the magnitude is 1. So we just utilize what we have learned from here, and just also utilize the things that we have learned, the properties of derivatives. So the magnitude is not easy to calculate, but if you do the squaring, the right hand side is the same thing, right? So what do you know? So you know 1 equals to the magnitude of t squared. And you actually also know that this is t starting with itself. Right? So the middle expression is going to be hard to do the derivative. But now if you have t starting with itself, then the derivative of this is not difficult to find. Okay. Thus, taking derivatives dt on both sides, we have So the left hand side is 1, you take the derivative with respect to t, it doesn't change, right? So the function value doesn't change, so the derivative is 0. The derivative of constant is 0. And now the right hand side, we have the derivative of t, cap t starting with itself, okay? Then we can utilize what we have learned about the derivative of the dot product, okay? So if you remember, that's actually the first derivative, the derivative of the first times the second, plus the first times the derivative of the second. And now the multiplication is the dot, okay? So basically we just write it down. So the derivative of the first, cap t prime, starting with cap t, plus the first, starting with the second. So that's good. Now we're actually getting to the punchline, right? We also notice that the dot product is commutative. Okay, so you see these two are essentially identical. Okay? So t dot t prime equals to t prime dot t prime. So and what do we want? We want t dotting t prime, right? So we just flip the order of the first expression here. So this is t dot t prime. And the second expression we just don't change. So this is exactly two copies of the same expression. And on the most left end, that's 0. On the right hand side, we have now what we want. Okay, so therefore, dividing both sides by 2, we'll get cap t, starting with its rate of change, cap t prime is 0. Okay, so you see, regardless of the curve, regardless of the input time point t, it's always true. Okay, and we do see that this is resulted from the fact that the unit tangent direction has a magnitude of 1, right? So the point here is that this is always true regardless of the curve, as long as your t and t prime, they are well defined. So sometimes it may be helpful for you to utilize it and simplify your calculations. Okay. Right, so that's the end of this section. So any questions so far?